Hello, my dear students. It's morning, 10 o'clock in Patna. We are in lecture number 15 now. Lecture 15 of chapter 1 of unit electrostatic. In last class, student, we have studied about, in last lecture, we have discussed about the electric flux and Gauss law. In very hurry, we have studied about the Gauss law. Today, we'll take a simple example. I'm recalling you the Gauss law. If it is point charge and it is enclosed within this Gaussian surface, it is not mandatory that the Gaussian surface should be this sphere, but for symmetricity, we use symmetric body to find the flux and electric field. Here, student, Gauss law is used to find electric field. Remember, Gauss law is used to find the electric field. Although we are having already the concept of flux and how to find the flux. So, Gauss has given this law to find the electric field. Electric field we have calculated, for example, for ring and rod. Okay, we have calculated, but here this particular law will simplify. It will simplify to find the electric field. Here, this charge is enclosed within this Gaussian surface. This was considered the Gaussian surface, and it will leave the. Remember, this is the imaginary surface. Please don't compare this imaginary surface with the conductor. Say whether this was the conductor or anything else. No, it is the Gaussian surface and imaginary. We are thinking actually it is a surface, and the Gaussian surface should be in such a way. This surface should enclose the charge in such a way like a balloon encloses the chocolate. Okay. Now, this is the charge, and this Gaussian surface encounter this electric field lines. We have studied according to this Gauss law, the net flux will be equal to 1 by epsilon naught times the Q enclosed. Okay, Q enclosed, that is the enclosed charge within this Gaussian surface. On the basis of this concept, we will take the very simple example today, student. Here, one example I am giving you to just explore your concept about the Gauss law. Suppose, here the example. This is a charge plus Q, okay, plus Q, and this is the minus Q. One Gaussian surface, this one. Another Gaussian surface is this one. So, Gaussian surface 1, Gaussian surface 2, and another Gaussian surface is this one. Okay, this is the Gaussian surface 3. This Gaussian surface 3 is enclosed the system of these two charges. Like this is the dipole. Since here the charge, two charges are separated by what distance, I'm not telling you. If this distance is very small, the charges, point charges of same magnitude here, although I am representing here the plus Q and minus Q. If this distance would be very small, then this will be considered as the dipole. But this Gaussian surface enclosing the two charges, the Gaussian surface 1 enclosing only the positive charge, Gaussian surface 2 is enclosing only the negative charge. Then you have to find the, or you have to apply the, here in example we are studying, apply the Gauss law. That's it. Okay, you have to apply the Gauss law, student. Here, for Gaussian surface 1, you can write the phi 1, it is as 1 by epsilon naught Q enclosed. How much it is? It is plus Q. So, it will be Q by epsilon naught. For Gaussian surface 2, here the phi 2, it is 1 by minus Q q by epsilon naught. Remember, this positive or negative sign will give you whether the flux is inward or outward, nothing else. Since it is the scalar quantity, only the counting, so it has nothing to take if it is plus or minus. For the counting, 2, -2 and +2 will be same. If we are taking the origin, we are moving rightward, the +2, and leftward as -2, but the counting will not change. So the such concept we are using here for the scalar quantity. For Gaussian surface 3, here the flux will be 1 by epsilon naught times the net charge. How much it is? 0. So the flux will be 0. So for this Gaussian surface, the total field lines live by this positive charge. It will be except by the negative charge, and this particular Gaussian surface will not encounter any field lines, net field lines, or if any field lines is moving out, then the same magnetic field lines will move in, and the net flux, that is the outward and inward, will be equal with the opposite sign, and the net will be 0. So this is the simple example how you have to apply the Gauss law, student. Now, as I told you in last lecture that in next lecture I'll prove this Gauss law. So today we are starting the lecture with this example, and then after with the proof of Gauss law. Proof. Actually, student, we so not the prove any law. Already law itself is been proved, but we are getting here mathematically how to represent the Gauss law. Remember how we can mathematically represent the Gauss law. Okay, suppose this is a charge and it is enclosed by any type of surface area. Here, from this charge at a distance r, this distance is r, a surface we are taking over here. This is the surface and the area vector in this direction. This is the area vector, and the radial vector will be this way. This is the theta. Okay, student? And so charge is situated. This is not the symmetric body. Now, using the concept of flux, as we know that the flux can be written at the E dot A. We haven't studied already. Okay, as we know that phi, it is equals to E dot A for this elemental surface. Here the area we have been written. We can write the dA also. Nothing too very difficult. Here the dA you can also write. Now, electric field at this point at which the surface area we have been taken, the electric field due to this point charge, we can write, if it is the charge, point charge, and at distance r, we can write the electric field as k q over r square. Am I right? And the direction along the r cap dot area vector. Okay, A or dA, if we are writing as dA. All right, now we can write here k q into dA dot r. dA dot r or r dot dA will be equal. A dot b equals to b dot a divided by r square. Now try to recall the solid angle, student, whether this is the equation we have been used for the solid angle. And solid angle, since this particular shape is enclosed this charge completely, it means we have to take the solid angle for this particular body, the solid angle around the total around the solid angle about this point. And we know that the total solid angle about any point is how much? It is r square, sorry, 4 pi. We have studied. So we can write here the k, how much it is? 1 by 4 pi epsilon naught into q. This is the k into q into 4 pi. This will be cancelled out, 4 pi, and we'll have the q by epsilon naught. Which charge we are getting here? This q is nothing but the total charge which is enclosed within this surface, and this surface is Gaussian surface, student. So the net flux we are getting here, the phi is equals to phi is equals to q by epsilon naught. Actually this was the Gauss law. So we have proved, or mathematically we have been represented here the Gauss law. The next question in your exam, you might be asked, student, let me wrap this one, to prove the Coulomb's law, okay, using this Gauss law. How will you prove? So the next question for your board exam, Coulomb's law using Gauss law. Actually student, Coulomb's law we have used, and this Coulomb's law gives the force between 2-point charges. If the 2-point charges are placed at certain distance, then the force of attraction or repulsion between that two charges can be represented as the k q1 q2 by r square. The same we are going to obtain here. Okay, so we take charge within this sphere. Okay, at the center we have been placed a positive charge. The radius is r. Suppose if we are considering this more elemental surface area, the area vector dA will be in this direction and the area vector will be radially outward. Now we are going to find here, we are going to represent or prove Coulomb's law using this Gauss law. According to Gauss law, student, what we can write? According to Gauss law, we can write the total flux encountered by this small area. Okay, this small area dA can be written at the surface integral of electric field. We can write, and which is equals the 1 by epsilon times q enclosed. So we are using the Gauss law. And we have to move for the Coulomb's law. So according to Gauss law, we can write phi equals to surface integral E dot dA, which is equals q by epsilon naught. How much charge it is enclosed by this surface? Q. Okay, so the q enclosed by epsilon naught. Now E r cap here radially outward dot dA, again r cap, since this area vector is also in the same direction, is equals to q by epsilon naught. R dot r1, here the E will be taken out, and the integral of dA, it is q by epsilon naught. Now E times integral of dA. dA is the elementary surface area of this sphere, and what will be the integral whole amount of this surface area? It is 4 pi r square. This is the surface area of sphere, q by epsilon naught. So E will be how much? It is q by 4 pi epsilon naught into r square. Here the 4 pi epsilon naught into r square. So this is the equation 1. Okay student, now we are having the electric field, and this electric field, actually if we have been taken the surface area over here, if we will take the surface area over here, we will get the electric field over here also. It means this electric field is everywhere on the surface. And if we suppose any point charge is placed at the surface of this sphere, remember there will be number of questions you will find by this concept also. We placed a small charge q here at the surface. It means this charge is placed, remember this is the imaginary surface, Gaussian surface we have been taken. This is the Gaussian surface. Now we placed a point charge at this surface. Can you write down over here? Erasing. Okay. Now, if a point charge, if a charge is placed at the surface, at the surface. If any charge placed at the surface, it means in presence of electric field. Here the electric field, and electric field how much? It is q by 4 pi epsilon naught r square. Any charge placed in electric field, it experiences a force, and that force can be written as the q times E in which it is placed. Okay, since it is the positive charge, if we are considering positive charge, then the force will give you the direction, and the direction of force will be again radially outward. Okay, so q times E, so we can write here the q times q by 4 pi epsilon naught r square, and this can be also written as 1 by 4 pi epsilon naught can be written as the k, q1 that is the q, q2 that is another q, divided by r square. So this is the Coulomb's law. We have been proved here the Coulomb's law. This is the Coulomb's law. We have been proved here using Gauss law. So this is the important question. You might be asked to prove the Coulomb's law using Gauss law, student. Okay. Student, if you will ask to find the electric field using this Gauss law, the same concept you will use till that equation 1. Okay, for 3 marks or 2 marks in board, several times this question has been asked. Okay, now let we discuss few examples on electric flux and Gauss law. Okay, student. Suppose this is a Gaussian surface and a charge is placed over here, Q. Now the question is asking, calculate the flux by this sphere. You have to find the flux since it will leave the field lines. Yes, this is the field lines, and you have to find and you have to count the number of field lines encountered by this sphere. What will be the answer? And the answer is very simple, student. The flux will be how much? It is 0. Why? Using Gauss law, we know that the phi can be written the 1 by epsilon naught times q enclosed. That is, we are applying the Gauss law for this particular body and charge inside the body. But here the charge inside the body is 0 because Q enclosed is how much? 0. So the phi will be also 0. Very simple. So you can write here the flux will be 0. Any charge outside the body will give net flux 0 if the body is completely closed. Remember, outside charge will give you the flux 0 if body is completely closed. Okay, student. Now the another question, that is the example. If it is charge enclosed by the sphere of radius r, now you have been asked to find the flux by this particular sphere. What will be the flux by this sphere? The flux phi is very easy. You can write q by epsilon naught. Yes, this is the answer of radius r. Now the question, if we will double the radius of Gaussian surface, with what factor flux will change? If we'll increase the surface area of the sphere, whether this will encounter more electric field lines, how electric flux will change? This is the question, and the answer is it will not encounter more electric field lines because the sphere is not responsible to create the electric field lines. Electric field lines is created by this charge, and charge has nothing to take if the surface area is increasing or decreasing. Okay, it's very simple. If you are inside the home and home is little or very small, it doesn't matter you are 1 or 5. If the shape or the size of home will increase, I don't think that you will be 2 or 3 from 1, of course. So here the field lines will same, so the flux remain same. If you will increase the shape of or decrease the radius of the Gaussian surface, the flux remain same. The flux will not change. Okay, student. Now the next question, next example. Here, hemisphere. Okay, and it is open. And a charge is placed at the center. Charge is Q. Remember, this hemisphere is open from its open face. This is diagram 1. Now again hemisphere, and this hemisphere is closed and the charge is placed just outside above this closed surface. This charge is placed and this is closed hemisphere. Now third case, this is the second diagram. Now the third case, again this hemisphere, and now this hemisphere is again closed. Now the charge is placed just inside. Okay, just inside. This is just outside, just outside, just inside, and it is open and charge is placed at center. You have to find flux for each cases 1, 2 and 3. Okay, in each case. So in this case the flux will be, so in first case 1, the flux will be how much? Since we cannot apply the Gauss law because this body is not closed. Remember, if this body is not closed, you cannot apply the Gauss law because Gauss law applicable for the closed body. Okay, it should be 3-dimensional but closed body. Suppose charge is placed over here, then you have to first close this system. Here there was hemisphere, one hemisphere. Now we have been closed this body, but to completely close this sphere you require another hemisphere. It was not with you. You have been applied extra hemisphere. Now if this hemisphere is closed completely, this charge, the electric flux will be how much? For this first case we are solving, the electric flux will be now Q by epsilon naught. Okay, Q by epsilon naught. But you are not having the total sphere, you are having the half sphere, that is the hemisphere. So the flux will be for hemisphere you will have the flux just half as the total. It is Q by epsilon naught. So the answer will be half Q by epsilon naught. Now the second one. For this one, if you are finding electric flux for this closed body, since the charge is outside the body, Q enclosed will be how much? Again 0. And if Q enclosed is 0, then flux will be 0. Very simple. Third one, since here the body is closed and charge inside the hemisphere and the hemisphere is closed, if it is closed then you can apply the Gauss law. Here the Q enclosed how much? Again Q. So the phi will be how much? Q by epsilon naught. It is very simple. Okay. Now the next example. I hope you understand. If you are not getting, then you must leave a comment in comment box. Okay. Otherwise we'll discuss in classroom lecture program. And such type of question it is mentioned in my assignment also. Student, I hope that you are doing your assignment I have been given. Okay, the next example, student. kindly don't overlook the assignment. Assignment is very important. More than 80 questions are given in the assignment, and that will strengthen you for your exam. From basic question in assignment, from basic question I have been included, and the number of question I have been framed by myself, and that will help you to understand the concept of this topic. Okay, student. Now, one example we are taking from NCERT. This is NCERT problem. In NCERT, it is given if it is a plate of side A, a charge is placed above the plate at A by 2. A charge is Q. Remember, in NCERT, the values are given. The side is 10 centimeter, this charge is 10 picocoulomb or 5 picocoulomb, whatever. Okay. And you have to find the flux due to, or flux by this plate, a square plate. Okay. Find the flux by this square plate. Now, how will you solve this question? You have to find the flux. Okay. Here the charge, it is placed A by 2 above the center of this square plate. I'm giving you few minutes. Try to solve. Pause the video and try to solve. Now the answer, student. Try to understand carefully. You cannot apply here the Gauss law again because this charge is in open space. Of course, you are having a plate, but this charge is placed in open space. So kindly try to enclose this charge using the same symmetric plates. How many plates you require to close this charge of the same shape? Actually 6 plates, and it become now cube. One plate you have been given, but you have to construct new 6 plates to enclose this charge. Okay, in this way I have been enclosed this charge. Now I can apply the Gauss law because now this charge is enclosed within the cube, and the net charge, if it is closed, now our new Gaussian surface is this one. Okay, and the net flux will be how much? Q by epsilon naught. But this is not the answer actually. We don't have the total 6 phases, only we are having one phase, and this is the flux by 6 phase. Okay, so for the 6 phase, using unitary method, if the flux is Q by epsilon naught, then for one phase, okay, one phase you will have Q by 6 epsilon naught. So the flux by one phase, it is 1 by 6 times epsilon naught. This is the answer. Okay, student, I hope that you are able to understand. Now this is your homework. If you are able to understand this one, 2 homework I'll give you. One, two plate, a square plate, okay, of side A, I have been adjoined in this way. To a square plate I have been adjoined, and a charge is placed A by 2 and A by 2 over here at A by 2 Q. Now you have to find the flux. And the second one, this is a little bit tough, but after few practice you can solve. This is a circular plate. This question we will discuss in classroom program, student. From center, a charge is placed at R, and the radius of this plate is also R. From by this square plate you have to find the flux. Okay, here by this 2 phases, adjoining 2 phases system, you have to find the total electric flux, and here you have to find the flux of this charge by this circular plate. Okay, student, that is all about the today lecture, which was very important. Thank you, my dear students.